Happy New Year, everyone. As we step into 2026, it's time to build bigger, better, and stronger literally. Let knowledge flow like a river, without any hindrance. Don't make it like a stagnant pool. Hello everyone. I'm PS Chatterjee, and a warm welcome back to today's DIY project. You are watching Structural Design Only, a channel with a different vision. Title of today's video is Short and Long RC Column Design, Automated 3D PU, MU Interaction Curve, Part 2, Excel Presentation. First, I will introduce you to the tables used to develop this sheet. There are 11 tables in total. This first table is our dashboard. Currently, the heading is Long Column Design by Stress Block and Axial Load with Biaxial Moments and 3D Interaction. This is because we just finished a long column design. Note that this heading adjusts dynamically from long column to short column based on the calculations. Now for table number 2. The headings here include Loads on Column, Selected Factored Loads and Load Case, and Limiting Moment Coefficient for Fy in newtons per square millimeter. There is also a check for uniaxial load and moment capacity. From the ultimate load case table, Excel will automatically select the governing load and fill the cells in light green. I explained how to build these two tables in my previous video, so I will focus on the new elements here. I will specifically explain the limiting moment coefficient, as the uniaxial load and moment capacity sections were covered previously. Moving to table number 3, Auto-generated basic parameters. You will see some parameters tagged with codes. These are the digital codes assigned to each specific parameter. Next, we have moments from eccentricity. Under this heading, we find the moment for first-order eccentricity. This moment is active only for short columns and is calculated using the working load. Next, we calculate the moment from additional eccentricity, which is a function of the column dimensions and the effective height. We also calculate the minimum moment by multiplying the factored load by the minimum eccentricity. Following this, we find the additional moments by multiplying the factored load by the additional eccentricity. Finally, we have the table for conversion coefficients for factored to working loads and moments. This table provides the specific coefficients needed to convert your factored loads back to working loads. The next table is titled, Distribution of Column Bars along the X-axis and Z-axis. This is one of the most vital components of the design. To truly understand how this works, we need to look at it in depth, so I will set aside time to explain this in detail later in the video. This table covers bar numbers, center to center distance, and clear spacing of bars. These values play a crucial role in our design. We use the center to center distance to calculate the effective modulus of elasticity of the column section, or EEFF. We also know that minimum clear spacing is essential for bonding integrity between the steel and concrete. Generally, this should be 1.5 to 2 times the maximum size of the coarse aggregate. In this calculation, I have used a 20 mm aggregate, resulting in a minimum clear spacing of 30 mm. Next, you will see the column end condition K-factor table. This provides the effective length factor based on your selected end conditions. Finally, the distribution table acts as the backup for the bar distribution drop-down menu found in our dashboard. Now we come to 3 vital, interconnected tables. These covers the radius of gyration of the bars in the x-axis and z-axis, the total moment of inertia of the bars, the effective moment of inertia, and Euler's buckling load capacity. We will calculate the buckling load, PCR, in kilonewtons, and finally, the equivalent buckling load, PCR equi. For long column design, the equivalent buckling load is critical, as our axial load, Pu, must be less than this value. This is a primary reference point that helps us treat a long column as an equivalent short column. Developing this table requires special care, and we will walk through it carefully in the second half of this video. The title of our next table is Calculation for Moment Magnification in both the x direction and z direction. This is another essential part of the design process. Since this is just a primary introduction, we will dive into the detailed calculations later in this tutorial. Next, we see 2 more interconnected tables, effective strain, stress, and load on column bars along the x-axis, and the normalized ratio of Pu and Mux for the 3D interaction. These tables are fundamental for understanding how the bars respond to axial loads and moments. We will explore these in detail shortly. Following that, we have the tables for concrete compression load from the stress block along the z-axis, and the normalized ratio for the 3D interaction of Muz and Pu. Like the previous sections, this is a complex area that we will cover thoroughly in the step-by-step portion of the video. Finally, we will create an automated interaction curve. This curve visualizes the available moments with respect to our calculated axial load, Pu. You will see 2 distinct curves here, one for available moments in the x direction and another for the z direction. Now, if you find this material helpful and informative, please give this video a big thumbs up. If you find any technical mistakes, please feel free to leave a dislike, but I ask that you provide a comment explaining why. A dislike without an explanation is like a punishment without a judgment, and your feedback helps me improve the content. Sharing knowledge is the best way to enhance it. If you have colleagues or engineering friends who would benefit from this, please share the link with them. If you would like to support my honest effort in creating these tutorials, please subscribe to the channel. Most importantly, don't forget to watch the rest of this video for the full technical breakdown. Next up, let's check out the new look for our sheet. The real star here is the dashboard, which switches between short and long column logic based on IS 456. I've added this formula box at the top to make things transparent, just pick an item from the drop-down, and you'll see the exact logic used. Are you ready to feel the thunder? Let's dive in. Selected load and moments. In this section, we have selected load PU, moments MUX and MUZ, and the selected load case. Now, I am selecting selected load PU under selected load and moments. You can see the formula is simply equal to PU underscore elected. The defined name of this cell is PU. Moment around X. Next, for the selected moment around X, it equals absolute, MUX underscore elected. The defined name of this cell is MUI underscore X. Moment around Z. Similarly, moment around Z or MUZ equals absolute, MUZ underscore elected. The defined name of this cell is MUI underscore Z. Selected load case. To finish this section, I am selecting selected load case, and the formula is equal to L underscore C. These represent the ultimate loads and the specific load case number used for the analysis. Capacity-based design. Under the capacity-based design heading, let's look at the math. Axial load capacity. First, I am selecting the formula for axial load capacity. The defined name of this cell is PU underscore cap. The formula is equal to 0.4 times FCK times AC underscore GR plus 0.67 times FY times A underscore SC underscore provided, all divided by 1000. Here, FCK and Fy are the characteristic strengths of the concrete and steel, AC underscore GR is the gross area of the concrete, and A underscore SC underscore provided is the area of steel we put in. Equivalent moment. The defined name of this cell is MU underscore EQ1. The formula in this cell is equal to the square root of the square of MUX plus the square of MUZ. Moment capacity around the x-axis. Now, look at moment capacity around the x-axis. The defined name of this cell is MU underscore cap X. The formula is PU underscore design times D underscore X divided by 2, minus EA underscore X, then divided by 1000. We then add 0.87 times Fy times A underscore SC underscore provided times D underscore EFF minus D underscore X divided by 2, and the whole thing is divided by 1,000,000. Here, D underscore X and D underscore EFF are the overall column dimension and effective depth of the column in the X direction. Moment capacity around the Z-axis. The defined name of this cell is MU underscore cap Z. Similar logic applies for the moment capacity around the Z-axis, swapping our depth for width and the corresponding eccentricity. The formula is PU underscore design times B underscore Z divided by 2, minus EA underscore Z, then divided by 1000. We then add 0.87 times Fy times A underscore SC underscore provided times B underscore EFF minus B underscore Z divided by 2, and the whole thing is divided by 1,000,000. Here, B underscore Z and B underscore EFF are the overall column dimension and effective depth of the column in the Z direction. Safety checks. The safety checks are where the OK happens. The formula for check for load, PU, is a simple if statement. If PU underscore cap is greater than or equal to PU, then display OK, otherwise, check. Safety check for moment around the x-axis. The formula for check for moment is equal to, if mu underscore cap x is greater than or equal to mui underscore x, then OK, otherwise check. Safety check for moment around the z-axis. The formula for check for moment is equal to, if mu underscore cap z is greater than or equal to mui underscore z, then OK, otherwise check. We apply this same logic to both the x and z moments. It's an instant verification that our capacity stays ahead of our applied loads. 02 design loads for long column. Now we are seeing a heading 02 design loads for long column. This heading will automatically change from 02 design loads for long column to 01 design loads for short column when Excel finds the column is a short column. To do that, the formula I have typed for the heading is equal to if slenderness is less than or equal to 12, 01 design loads for short column, otherwise 02 design loads for long column. Here, slenderness is the defined name of the slenderness ratio cell. Axial load. Under this heading, the formula for load PU is equal to PU, same as the formula for selected load PU. The defined name of the cell is PU underscore design. Check for axial load. The formula is equals to if n long underscore short equals to 2 PU underscore design less than or equals to P underscore CR, then OK, if n long underscore short equals to 1 PU underscore design equals to PU, then OK, otherwise, check. Simple meaning, in this Excel sheet, the axial load check is performed using an if with n logical formula. First, Excel identifies whether the column is a short column or a long column using the variable long underscore short. If long underscore short equals to 2, it means the column is a long column. In that case, Excel compares the design axial load, PU underscore design, with the Euler's critical buckling load, P underscore CR. If P underscore CR is greater than or equal to PU underscore design, the cell will display OK. Otherwise, it will display check. Similarly, if long underscore short equals 1, it indicates a short column. For a short column, Excel checks whether the design axial load PU underscore design is equal to the applied axial load PU. If this condition is satisfied, Excel displays OK, otherwise, it displays check. In this way, Excel automatically verifies the axial load safety based on whether the column is short or long. Formula for the title, magnified moment around x-axis. Below this PU, we see moment MUX magna. This will also change from moment MUX magna to moment MUX when Excel finds the column is a short column. The formula is equal to if long underscore short is equal to 2, moment MUX magna, if long underscore short is equal to 1, moment MUX. Here, long underscore short is the defined name of the digital code for long and short columns, 1 for short, 2 for long. We already know that for long column design, we have to magnify our calculated ultimate moments to convert the long column to an equivalent short column. Formula for magnified moment around x-axis. Beside this, we bring the calculated value of magnified moment around x-axis MUX magna, and the formula to type here is equal to MUX underscore mag. Check for magnified moment around x-axis. Next to this, we have a check for this moment, and the formula is equal to if MUX equals n.a, then n.a, if absolute MUX underscore design is greater than absolute MUX underscore mag, then OK, otherwise check. Formula for the title, magnified moment around z-axis. The formula for the title moment MUZ magna is equal to if long underscore short equals 2, moment MUZ magna, if long underscore short equals 1, moment MUZ. Formula for magnified moment around z-axis. In the next cell, we type the formula, equal to MUZ underscore mag. The defined name of the cell is MUZ. Check for magnified moment around z-axis. Now, I am changing the formula to check MUZ underscore mag, and the formula is equal to if MUZ equals n.a, then n.a, if absolute MUZ underscore design is greater than absolute MUZ underscore mag, then OK, otherwise check. Same as before, here NA stands for not applicable. Moment from 3D interaction in X direction. In this final section, we will bring the calculated available moment around the X direction from the 3D interaction graph, and the formula is equal to MUX underscore available. Check for available moment around X-axis. In the next cell, type the formula, equal to if, or, check underscore 04 equals n.a, check underscore 05 equals n.a, KAX is greater than 1.14, if, check underscore 10 equals O.k, then O.k, otherwise check. Moment from 3D interaction in Z direction. Similarly, we bring the calculated available moment around the Z direction from the 3D interaction graph, and the formula is equal to MUZ underscore available. Check for available moment around Z-axis. Once again, in the next cell, type the formula, equal to if, or, check underscore 04 equals n.a, check underscore 05 equals n.a, KAZ is greater than 1.0, if, check underscore 11 equals O.k, then O.k, otherwise check. Here, check underscore 04 and check underscore 05 are the defined names for MUX and MUZ respectively. Check_10 and check_11 are the defined names of checks for available moments and calculated moments around the X and Z axes. Checklist for final design. Now we are shifting our views to the checklist for final design. Under this section, we are going to check the percentage of steel provided, minimum clear spacing of bars, buckling load, MUX design, MUS design, and uniaxial moment capacity. Percentage of steel provided, the formula is equal to 100 times A_SC_ provided, divided by B_Z times dx. The defined name of this cell is P_C_ provided. Check for percentage of steel provided. Beside this cell, we will check the percentage of steel provided. The formula is equal to if, or, P_C_ provided is less than 0.8%, P_C_ provided is greater than 6%, check, otherwise OK. Minimum clear spacing of bars, the formula is equal to the minimum of clear_spacing_x_dir and clear_spacing_z_dir. Check for minimum clear spacing of bars. Beside this cell, we will check the minimum clear spacing of bars. The formula is equal to if J15 is greater than or equal to 35, OK, otherwise check. Here, in cell J15, we have the calculated minimum clear spacing of bars, and 35 means the minimum requirement is 35 millimeters. We know the required minimum clear spacing is 1.5 to 2 times the maximum size of coarse aggregate. If we consider the maximum size of the coarse aggregate to be 20 millimeters, then this value will be between 30 to 40 millimeters. Here, I have considered 35 millimeters. Buckling load, the formula is equal to if long_short is equal to 1, not required, otherwise P_CR. The simple meaning is, if Excel finds the column is a short column, it will type not required, otherwise, Excel will put the calculated value of P_CR in this cell. P_CR is the name of the cell for the calculated value of buckling load. Check for buckling load. Beside the cell for buckling load, Excel will check the value. The formula is equal to if, or, J16 equals not required, J16 is greater than PU_design, OK, otherwise check. This means if Excel finds the statement not required in cell J16, or a value greater than PU_design, it will type OK, otherwise, it will type check. Here, cell J16 refers to the calculated buckling load or P_CR. MUX design, the formula is equal to if long_short is equal to 1, MUX, otherwise MUX_design. Simply put, if Excel finds the column is a short column, it will use the value of MUX, otherwise, Excel will put the calculated value of MUX_design in this cell. Check for MUX design. Beside the value of MUX design is the checkpoint. The formula is equal to if J17 is greater than or equal to MUX, OK, otherwise check. If cell J17 is greater than or equal to MUX, it will type OK, otherwise, it will type check. MUS design, the formula is equal to if long underscore short is equal to 1, MUZ, otherwise MUZ underscore design. If Excel finds the column is a short column, it will use the value of MUZ, otherwise, Excel will put the calculated value of MUZ underscore design in this cell. Check for MUZ design, beside the value of MUZ design is its checkpoint. The formula is equal to if J18 is greater than or equal to MUZ, OK, otherwise check. If cell J18 is greater than or equal to MUZ, it will type OK, otherwise, it will type check. Uniaxial moment capacity, the formula is equal to I underscore ratio. Here, I underscore ratio is the interaction ratio of uniaxial load and moment capacity, or the 2D interaction of load and moments. Check for uniaxial moment capacity, we know that this ratio must be less than or equal to 1. The formula is equal to if J19 is less than or equal to 1, O.K, otherwise check. Final check. Now, we are going to finish this dashboard with these final formulas. This formula will tell the story of our design. Here we will find the type of the column, such as long or short column, and the final status of the design. The formula is a combination of if, and, equals, and not equals. It consists of 4 parts of logic. First portion, if, and long underscore short equals 2, and all check cells K14, K15, K11, K16, K17, K18, K19, and K12 equal OK, then display long column design OK. Second portion, if, and long underscore short equals 2, and any of those cells do not equal OK, then display check long column design. Third portion, if, and long underscore short equals 1, and all check cells equal OK, then display short column design OK. Fourth portion, if, and long underscore short equals 1, and any of those cells do not equal OK, then display check short column design. Now, let's move to table number 2. Now, we are looking at the second section, titled, Loads on Column and Check for Uniaxial Load and Moment Capacity. Under this heading, we have 3 separate tables. These are, ultimate loads and load case, selected factored loads and load case. Check for uniaxial load and moment capacity. First, let us look at the ultimate loads and load case table. The data in this table is generated by your design software. When you bring these values into Excel, it is very important to use the path, paste special and values. If you do not follow this method, the embedded formulas in the Excel sheet will be deleted, and the sheet will not function properly. Next, let us look at the selected factored loads and load case table. Here, Excel automatically identifies the maximum effective design loads from the complete list. If you want to understand the methodology behind this table, please refer to my previous video titled, Column Design Without the Charts of SP16. Now, let us see a live demonstration. At present, in the main table, load case 209 is highlighted in light green. This color indicates that this is the selected load case. For this case, the axial load Pu is 1100 kilonewtons. The moment MUX is 50 kilonewton meters. And the moment MUZ is 4 kilonewton meters. You can see these same values appearing automatically in the selected factored loads table. Now, I will change the value of Pu for load case 209 from 1100 to 500 kilonewtons. Observe the change carefully. The light green color has now moved from row 209 to load case 213. Row 209 is now white. At the same time, the selected factored loads table has updated automatically. It now shows the values for load case 213. The axial load Pu is 916.886 kilonewtons. The moment MUX is 65.887 kilonewton meters. And the moment MUZ is minus 3.574 kilonewton meters. In this way, Excel automatically captures the most critical load case, ensuring that your column design is always based on the maximum effective loads. Now, we are going to check the uniaxial load and moment capacity for the interaction of Pu and Mu. This table is applicable for both short and long columns. Based on our design parameters, Excel will automatically switch between short column and long column checks. Since we are checking the interaction for long columns, we must determine the moment magnification ratios in both directions. These directions are X direction and Z direction. Moment magnification ratio is applicable only to long columns. Excel performs this calculation automatically, so no manual input is required. First, let us look at the moment magnification ratio in the X direction, denoted as CMX. The formula is, if long underscore short is equal to 2, then MUX underscore mag, divided by MUI underscore X. Otherwise, the value is NA. Here, MUI underscore X is the initial calculated moment, and MUX underscore mag is the magnified moment. The defined name of this cell is CM underscore X. Similarly, the moment magnification ratio in the Z direction is CMZ. The formula is, if long underscore short is equal to 2, then MUZ underscore mag divided by MUI underscore Z. Otherwise, the value is NA. Here, NA means not applicable. The defined name of this cell is CM underscore Z. Next, we see the representative cells for MUX and MUZ. These cells display our current design moments, MUX and MUZ, respectively. Now, we calculate the ultimate maximum moment capacities. These are MUX1 and MUZ1. Let us first see the formula for MUX1. If long underscore short is equal to 1, we use 0.138 times FCK times BZ times the square of D underscore EFF divided by 10 to the power of 6. However, if long underscore short is equal to 2, we take the same formula and multiply it by CMX. The defined name of the cell is MUX underscore 01. Now, let us see the formula for MUZ1. If long underscore short is equal to 1, we use 0.138 times FCK times dx times the square of B underscore EFF divided by 10 to the power of 6. If long underscore short is equal to 2, this value is multiplied by CMZ. The defined name of the cell is MUZ underscore 1. As you can see, the formulas for short and long columns are almost identical. The only difference is that for long columns, we multiply the base capacity by the moment magnification ratios, CMX and CMZ. Now, we calculate the ratio of MUX and MUX1. The formula is very simple. It is equal to MUX divided by MUX underscore 01. The defined name of the cell is MUX underscore 1. Finally, we calculate the ratio of MUZ and MUZ1. Again, the formula is simple. It is equal to MUZ divided by MUZ underscore 1. The defined name of the cell is MUZ underscore 1. Now, we are going to see the formulas for calculated axial load on column, PU. This is a very simple formula. It is equal to PU. Actually, this cell represents our selected design axial load, PU. Next to this, we are going to see the formula for PUZ. PUZ is the maximum axial load that a column can carry. The formula is 0.4 times FCK times AC underscore NT, plus 0.67 times Fy times ASC provided, whole divided by 1000. Here, AC underscore NT is the net area of concrete, not the gross area. And ASC provided is the area of steel provided. The defined name of the cell is PU underscore Z. After this, we calculate the ratio of PU and PUZ. The formula is PU divided by PUZ. The defined name of the cell is PU underscore PUZ. Now, we move to the formula for alpha n. Alpha n is also known as the biaxial interaction exponent. This value is used in the biaxial moment interaction equation. The formula for alpha n is as follows. If PU underscore PUZ is less than or equal to 0.2, then alpha n is equal to 1. If PU underscore PUZ is greater than or equal to 0.8, then alpha n is equal to 2. Otherwise, alpha n is equal to 1 plus PU underscore PUZ minus 0.2, divided by 0.6. The defined name of the cell is _n. Next, we calculate the interaction ratio. The formula is mux_mux1 to the power of _n plus muz_muz1 to the power of _n. The defined name of the cell is I_ratio. For a safe and secure design, this interaction ratio must be less than or equal to 1. Now, we check the value of I_ratio. If I_ratio is less than or equal to 1, Excel will display OK. Otherwise, Excel will display check. The defined name of the cell is check_09. Now we are on the last line of this table, titled, Loads on column and check for uniaxial load and moment capacity. Here, we see a dynamic statement. Interaction ratio less than or equal to 1. Uniaxial moment capacity, OK. This statement explains why the interaction check is satisfied. The formula is, if I_ratio is less than or equal to 1, Excel will show, uniaxial moment capacity, OK. Otherwise, Excel will show, I_ratio greater than 1. Check uniaxial moment capacity. Now, let us move to the next table. Auto-generated basic parameters. Now, we are looking at the table with the heading, Auto-generated basic parameters, moments from eccentricity, and limiting moment coefficient for Fy. First, I will discuss auto-generated basic parameters. Bar distribution code. Our first parameter is the bar distribution code. This code is directly linked to the number of bars and distribution section of the dashboard. In the dashboard, under the bar distribution section, we have three options: 0, 1 equal, 0, 2 x direction, 0, 3 z direction. From this combination of number and text, we need to extract a numeric code based only on the number. To achieve this, we use the formula, equals to, value, mid, D23, 2, 1. Here, D23 is the cell where the bar distribution type is selected. The simple meaning of this formula is, the mid function extracts the numeric character from the text, which can be 1, 2, or 3. The value function then converts this numeric text into an actual number. The defined name for the cell is bar_distribution. Braced or unbraced column code. Next, we move to the braced or unbraced column code. The formula used here is, equals to, value, mid, B18, 2, 1. Cell B18 contains the drop-down selection for the column end condition, with two options, 0, 1 braced, 0, 2 unbraced. The functionality of this formula is exactly the same as the previous one. Mid extracts the numeric character, value converts it into a number. The defined name of the cell is braced_unbraced. Column end condition and k-factor code. Now, let us understand the formula for the column end condition and effective length factor, or K factor. The formula used is, equals to, if, braced underscore unbraced equals to, 1, VLOOKUP, B17, G74 I78, 2, 0, if, braced underscore unbraced equals to, 2, VLOOKUP, B17, G74 I78, 3, 0. This formula uses nested if functions along with VLOOKUP. B17 is the lookup value. In the dashboard, under joint condition of column, we have a drop-down menu with 5 options, starting from 0, 1 fixed end, up to 0, 5 pinned, roller end. The range G74 to I78 is the table array. This table is located under the section Table for bar numbers and center-to-center distance and clear spacing of bars. Column 2 of the table contains values for braced columns. Column 3 contains values for unbraced columns. The last argument 0 in the VLOOKUP ensures an exact match. The defined name of the cell is K. Short and long column code. Next is the formula for the short and long column code. The formula is, equals to, value, mid, H7, 2, 1. Cell H7 is a dynamic heading on the dashboard that changes between short column and long column. From this heading, the formula extracts the numeric code that identifies whether the column is short or long. The defined name of the cell is long_short. Creep code. Finally, let us look at the creep code. The formula used is, equals to, value, mid, D19, 1, 1. Cell D19 contains the drop-down menu for the creep coefficient. The available options are, 0 short-term, 1 moderate, 2 long-term, 3 severe. In this case, only one numeric character is present in text form. That is why the mid function extracts one character instead of two, unlike the previous cases. The defined name of the cell is creep_value. Now, we will see the simple calculation for area of each bar. The formula is 0.25 times pi times b_d to the power of 2. Here, b_d is the diameter of the reinforcement bar. The defined name of the cell is a_bar, and the unit is square millimeters. Next, we will see the calculation for area of total steel provided. The formula is, n times a_bar. Here, n is the number of bars provided. The defined name of the cell is as_provided, and the unit is square millimeters. Next, we will see the calculation for effective cover. The formula is, cc plus b_d divided by 2. Here, cc is the provided clear cover. The defined name of the cell is c_EFF, and the unit is millimeters. Now, it is time to calculate the effective width. The formula is, b_z minus, c_EFF. Here, b_z is the dimension of the column in the z direction. The defined name of the cell is B_EFF, and the unit is millimeters. After effective width, we will see the formula for effective depth. The formula is D_x minus C_EFF. Here, D_x is the dimension of the column in the x direction. The defined name of the cell is D_EFF, and the unit is millimeters. Now, we will calculate the gross area of concrete. The formula is D_x times B_z. The defined name of the cell is AC_GR, and the unit is square millimeters. We already know the values of gross area of concrete and area of total steel provided. Now, we will calculate the net area of concrete. The formula is AC_GR minus AS_ provided. The defined name of the cell is AC_NT, and the unit is square millimeters. Next, we will calculate the slenderness ratio of the column, denoted by the Greek letter lambda. The formula is 1000 times H_EFF divided by min, D_x, B_z. The defined name of the cell is slenderness. Since this is a ratio, it has no unit. In this section, our last parameter is the effective height of the column. Formula for effective height of the column is equals to K times H_sub. The defined name of the cell is H_EFF, and unit is meter. Now, the first parameter in this section is the allowable strain in concrete. The maximum allowable strain in concrete is a fixed value, and this value is 0.0035. Strain is generally denoted by the Greek letter epsilon. The defined name of the cell is E_cu. Since strain is a ratio, it has no unit. The second parameter is the allowable strain in steel. Similarly, the maximum allowable strain in steel is also a fixed value, and this value is 0.002. The defined name of the cell is E_SU. Again, since this is a strain value, it has no unit. Now, it is time to discuss moments from eccentricity. In this section, we have four components. First order eccentricity, additional eccentricity, minimum moment, and final moments. In this video, we will focus on the first two components. First order eccentricity. First order eccentricity means the eccentricity of load and moment due to working load and working moment. First order eccentricity along x-axis. The formula for first order eccentricity along the x-axis is equals to if long_short equals to 2 n/m 1000 times abs mui_z divided by k_moments divided by pu divided by k_load. The simple meaning of this formula is, for a long column, first order eccentricity is not applicable. For a short column, this formula calculates working moment about the z-axis divided by working axial load. Here, K underscore moments is the conversion factor to convert factored moment to working moment. K underscore load is the conversion factor to convert factored load to working load. I will explain K underscore moments and K underscore load in a later section. The defined name of the cell is E underscore X, and the unit is millimeters. First order eccentricity along z-axis. Next, the formula for first order eccentricity along the z-axis is equals to if long underscore short equals to 2 n slash 1000 times abs mui underscore x divided by k underscore moments divided by pu divided by k underscore load. The meaning of this formula is exactly the same as the previous one. For a long column, this value is not applicable. For a short column, it gives working moment about the x-axis divided by working axial load. Once again, K underscore moments converts factored moments to working moments. K underscore load converts factored loads to working loads. The defined name of the cell is E underscore Z, and the unit is millimeters. Additional eccentricity. Now, we move to additional eccentricity. Additional eccentricity along x-axis. The formula for additional eccentricity along the x-axis is equals to if long underscore short equals to 1 max 1000 times h underscore un underscore sub divided by 500 plus d underscore x divided by 30 20 if long underscore short equals to 2 max 1000 times h underscore un underscore sub divided by 500 plus d underscore x divided by 30 20 c underscore red times 1000 times h underscore eff to the power of 2 divided by 2000 times d underscore x error. The simple meaning of this formula is, if the column is a short column, the additional eccentricity is the maximum value between 1000 times unsupported height divided by 500 plus d underscore x divided by 30, and 20 millimeters. The defined name of the cell is EA underscore x and unit is millimeters. If the column is a long column, the additional eccentricity is the same maximum value as above, plus an additional term involving the limiting moment coefficient, denoted by C underscore red. Here, C underscore red is the limiting moment coefficient, which I will explain in the next section. Additional eccentricity along z-axis. Similarly, the formula for additional eccentricity along the z-axis is equals to if long underscore short equals to 1 max 1000 times h un underscore sub divided by 500 plus b underscore z divided by 30 20 if long underscore short equals to 2 max 1000 times h un underscore sub divided by 500 plus b underscore z divided by 30 20 c underscore red times 1000 times h underscore eff to the power of 2 divided by 2000 times b underscore z error. The logic and interpretation of this formula are exactly the same as the previous one, with d underscore x replaced by b underscore z. So, no further explanation is required here. The defined name of the cell is EA_Z and unit is millimeters. Minimum moment. Now, we will discuss the minimum moment. As per column design requirements, a minimum moment must always be considered, even if the calculated eccentricity is very small. Minimum moment about x-axis. The formula for minimum moment about the x-axis is Pu times Ea_x divided by 1000. Here, Pu is the factored axial load, in kilonewtons. Ea_x is the total eccentricity along the x-axis, in millimeters. Dividing by 1000 converts the moment from kilonewton millimeters to kilonewton meters. The defined name of the cell is MUX0 and unit is kilonewton meters. Minimum moment about z-axis. Similarly, the formula for minimum moment about the z-axis is Pu times Ea_z divided by 1000. Here, Ea_z is the total eccentricity along the z-axis, in millimeters. Once again, dividing by 1000 converts the value into kilonewton meters. The defined name of the cell is MUZ0 and unit is kilonewton meters. Final moments. Now, we will calculate the final design moments. The final moment is taken as the maximum value between the moment obtained from eccentricity and the minimum moment. Final moment about x-axis. The formula for final moment about the x-axis is max MUX_elected, MUX0. Here, MUX_elected is our calculated design moment. MUX0 is the minimum moment about the x-axis. The larger of these two values is selected as the final design moment. The defined name of the cell is MAX and unit is kilonewton meters. Final moment about z-axis. Similarly, the formula for final moment about the z-axis is max MUZ_elected, MUZ0. Here, MUZ_elected is our calculated design moment. MUZ0 is the minimum moment about the z-axis. Again, the maximum value is selected as the final design moment. The defined name of the cell is MAZ and unit is kilonewton meters. With this, the calculation of minimum moment and final design moment is complete. K_load and K_moments. Now, let us understand the purpose of K_load and K_moments. In our Excel calculation, all the applied loads and moments are factored values. However, first-order eccentricity is defined based on working loads and working moments, not on factored values. Therefore, we need conversion factors to move from factored quantities to working quantities. This requirement becomes especially important for load combinations such as 0.9 times Pu plus 1.50 times Mux plus 1.50 times Muz. This is where K_load and K_moments are used. K_load. K_load is the conversion coefficient for moments. It is used to convert factored load into working load moments. Mathematically, this is expressed as working load equals to factored load divided by K underscore load. In most practical cases, K underscore load is taken as 1.5, which corresponds to the usual load factor used in limit state design. The defined name of this cell is K underscore load. Sometimes, we assume that working load cases are completely abandoned in IS 456:2000. This is not true. Working load cases are, in fact, the foundation of our design philosophy. Formula for K underscore load. The Excel formula used for K underscore load is equals to if or L underscore C equals 201, L underscore C equals 206, L underscore C equals 207, L underscore C equals 208, L underscore C equals 209, 1.5, if, or, L underscore C equals 202, L underscore C equals 203, L underscore C equals 204, L underscore C equals 205, 1.2, if, or, L underscore C equals 210, L underscore C equals 211, L underscore C equals 212, L underscore C equals 213, 0.9. The simple meaning of this formula is, if the load case is 201 or 206 to 209, the conversion factor is 1.5, if the load case is 202 to 205, the conversion factor is 1.2, if the load case is 210 to 213, the conversion factor is 0.9. K underscore moments. Similarly, K underscore moments is the conversion coefficient for moments. The defined name of this cell is K underscore moments. Now, we are at the last explanation of this table, titled Limiting Moment Coefficient, CRED, for Fy. In this table, the first row represents Fy, that is, the characteristic strength of steel. The second row shows the corresponding values of the limiting moment coefficient, denoted as CRED. These values are fixed design parameters, and they are taken directly from design provisions. The values used in our Excel sheet are, for Fy equals to 250, CRED equals to 0.148, for Fy equals to 415, CRED equals to 0.138. For Fy equals to 500, CRED equals to 0.133. For Fy equals to 550, CRED equals to 0.130. For Fy equals to 600, CRED equals to 0.128. Selecting the limiting moment coefficient. At the last row of this table, next to the cell titled Selected Limiting Moment Coefficient, CRED, for Fy, we automatically select the appropriate value of CRED, based on the selected value of Fy. The formula used is, equals to, H lookup, Fy, $G $53 K $54, 2, 0. Explanation of the formula. The working of this formula is simple. Fy is the lookup value, representing the selected grade of steel. G53 to K54 is the table array, where the first row contains values of Fy and the second row contains the corresponding CRED values. The number 2 instructs Excel to return the value from the second row of the table. The final 0 ensures an exact match. About CRED, the defined name of the cell is C_red. CRED is a limiting moment coefficient used in the calculation of additional eccentricity for long columns. It acts purely as a multiplier in the additional eccentricity formula. Since it is a coefficient, CRED has no unit. We have already crossed the 1-hour mark. In today's world of shorts and reels, I honestly don't know how many of you will stay with me till the end of such a detailed session. But I truly believe this half knowledge can mislead, while complete understanding empowers. That is why I always choose detail over shortcuts, even if only a few committed learners are watching. At this point, I'll take a small pause, not to stop, but to prepare the next part with even more care. In the upcoming episode of Dynamically Interchangeable Short and Long RC Column Design on Excel, I'll demonstrate the remaining tables clearly, step by step, just as we have done so far. If you've stayed till here, thank you from the bottom of my heart. Your time, patience, and trust truly matter to me. And now, yes, it's time to perform a small YouTube ritual. Now, if you find this material helpful and informative, please give this video a big thumbs up. Sharing knowledge is the best way to enhance it. If you have colleagues or engineering friends who would benefit from this, please share the link with them. If you would like to support my honest effort in creating these tutorials, please subscribe to the channel. Most importantly, don't forget to watch the rest of this video for the full technical breakdown. If you feel any part of the explanation was weak or unclear, please use the dislike button without hesitation, but always share your reason in the comments. Sometimes disliking is more valuable than liking, because feedback helps us improve. A dislike without context, however, is a verdict without judgment. Once again, wishing everyone a very happy new year. As we step into 2026, let's continue learning, designing, and building bigger, better, and stronger, not only in structures, but also in knowledge.